Well, it is 4. Polling closes at 8. If you haven't voted, don't forget. Today we have John Palmore, who's a good friend of mine. I've known him for a number of years. I think we overlapped 2 years at Cornell. So I around the time I got to Cornell is when you joined, and then I was there for 2 years. So John was in the same research group as me. He was focused on numerical methods for gas liquid interfacial flows with phase change. And I often show his some of his work in my multi-phase course because it's some of the first results of an interface tracking method with phase change. This was a couple years ago now, but it's still very few groups doing this. So I think John finished his PhD from Cornell in 2018 and went on to be assistant professor at Virginia Tech. And then a couple months ago, or maybe a year ago, joined University of Washington. And I think we'll be seeing some of that work on interface tracking and also the ground-chain particle tracking in this talk.
Yeah. Yeah, thanks. All right, that was a great introduction. Thanks for inviting me here. Like I said, John Palmore. So I lead this research group. So this is an acronym. So you choose your acronym and then you choose the word, you get the letters. So my research group, we call it CAMPFIRE. And then the acronym is Combustion, Atomization, Multiphase, and Particulates Physics Research and Education Group. Which is an accurate description of everything that we do. And then we're going to talk about part of that, which I'm going to talk about. I decided to just abbreviate it as new strategies and results for water and droplet-laden flows. So CAMPFIRE, so this is most of the key personnel for CAMPFIRE. This photo is quite old. It's from back when we were at Virginia Tech. So it still has like the Virginia Tech mascot in the background there. And this is quite old, but it shows most of the key personnel. My 3 PhD students, Kyron, Meha, and Yushu, also myself, of course. And then I also had these 2 undergraduate students at the time, Duncan and Michelle. Most of the stuff that's going to be presented here today, or actually all of it, is going to be from Meha and Yushu, these people here. Okay. Challenge. All right, I like to start it off with a broad motivation. So I say, real fluid dynamics, real fluid flows are oftentimes, or maybe even almost exclusively, multi-phase flows. Not just engineering or science. I mean, some of the most famous pictures of art in the world are depicting multi-phase flow, or whether it's this type of free interface flow here with water and air and droplets, or whether it's the flow of clouds, which involves dust and droplets, particulates inside of air. And we're going to define this very broadly and say the multi-phase flow is a fluid problem consisting of 2 or more immiscible fluids. So the way that I would define it, free surface flows would also be a subcategory of this as well. In engineering, these occur in a lot of different various applications. But most commonly, you're going to see this in a situation where you need to have heat and or mass transfer. And then I just listed a couple of common engineering applications. So my background is more associated to this, which is combustion as it occurs, principally motivated by aviation. So you have like a fuel, which breaks into droplets, and then there's going to be gas around it. Fire suppression is another application you might think of. So here you have water droplets, in air. You can also talk about a lot of chemical engineering systems involve bubbles, where you have a liquid and then you use some bubble either for mass transfer or heat transfer inside of that system. And then you can also think about even blood flow, biomedical devices, biomedical engineering. You can think about this as being a multi-phase flow as well. You really have like a liquid, basically water, with things in it like sugars, cells, obviously, and proteins. So my background is more towards this spray combustion angle. So I'll talk about a lot of this stuff in a context that's most related to spray combustion. So in this context, I love this image that I've taken from Stanford, thanks Stanford, where they allow this liquid jet that's injected, breaks into droplets, droplets evaporate, and then the vapor, which is a gas, mixes with the air, which is a gas. That's the multi-phase aspect. And finally, combustion results. And And so this is like both multi-phase and multi-physics. There's different types of heat transfer, flow dynamics, chemical reactions going on. There's also multi-scale, right? It's like the combustor scale perspective of it, but also the scale of an individual droplet, which is much smaller. So multi-phase, multi-scale, multi-physics, a lot of things going on. All right, so a lot of what I talked about in my work is related to, again, this application of sprays. And one of the things I want to say is that as a matter of practice, the way that we understand sprays is by looking at the droplets, which consist of the spray, but there's a lot of dissonance between what we know about droplets and what's actually relevant for a real spray. So this slide is kind of highlighting some of the common points, right? So a lot of the theory of droplets, we're looking at either quiescent or a uniform flow around the droplet. Spray, actual spray is turbulent flow. A lot of the theory is looking at a spherical droplet. Actual droplets don't necessarily look spherical. So this is a very famous experiment, relatively low Reynolds number too. So not even like particularly high Reynolds number outlier type of situation. And it's showing the atomization or breakup of a liquid stream into droplets. And if you zoom in, you can see these not sphere shaped droplets, right? So droplets are not spherical. Another common assumption is that there's no flow inside of the droplet. There's no internal circulation, and that is violated. So the shear from the air onto the droplet will induce internal circulation. Another thing is people are usually, most of these theories are looking at isolated droplets. So this droplet is like the only thing in the entirety of the universe. There's no interactions with walls or other droplets. And that is not accurate for sprays. Sprays are a dense collection of droplets. And then the other thing, which is kind of a subtle thing, is that either of the theories are assuming droplets are infinitely small. And we're going to say, without explaining too much about this, that droplets can be of sizes that are relevant to the turbulence scale. So this parameter eta here is representing some type of turbulence length scale. But droplet sizes can be commensurate with turbulent length scales of the flow. So I'm going to claim that there's a gap in knowledge, let's say, between application and theory. It's largely driven by the fact that we need to know more about droplets, and that's also the goal of what we're mostly studying here. All right, so kind of the foundational idea here, or the approach that we have here, is that a lot of the spray kind of theory or droplet theory is basically of the form that your force or your evaporation rate or your drag or your lift or whatever is described by some type of gas phase boundary layer equation. So maybe depends on Reynolds number. If you're doing heat transfer, you might have something like Prandtl number, a heat transfer number, or a mass transfer number if you're doing heat or mass transfer. I mean, those things are important, but it's not the complete picture, right? So if you're doing a multi-phase flow, other things will be important that are related to the multi-phase flow. The density ratio between phases, the viscosity ratio between phases. This parameter, which is related to, it's called Weber number, which is related to the shape of the droplets. So we showed how those things deform when they're subjected to aerodynamic stresses. So that's captured in this parameter. And then in general, if you're dealing with a real turbulent flow, not uniform flow, so you're probably going to want something that will represent the non-uniformity of the flow, like a shear rate. So this is a shear rate, okay? And some of these phenomena have been studied. And so what we're doing is kind of improving upon it, kind of systematizing it in a generalistic formulation and continuing the study in these areas. Okay. So how I'm going to break up the rest of this is like, I'll briefly talk about the numerical methods that mostly developed during a PhD. Then we'll use those to investigate droplet evaporation and droplet drag. And then we'll kind of collect some of those results, think about them, and then explore the implications of that and drag of droplets and their dispersion inside of a turbulent flow field. It'll be homogeneous isotropic turbulence in this case, and then we will be done. Yeah, okay. So yeah, this section is mostly based on my PhD work, just reviewing the numerical method that I developed during my PhD. Right, so why do you want to simulate spray? Well, we talked before about the fact that it's multi-scale, multi-physics, multi-phase phenomena. Compared to experiments can be difficult because of the so-called high optical density of sprays, which makes it difficult to use optical measurement techniques. And then even if you can make those type of measurements, sometimes you just want a type of data that's more amenable to CFD, like field data, as opposed to like isolated point data. Some of the numerical challenges, well, between the two phases, liquid and gas, you got vastly different fluid properties like density, viscosity, et cetera. This is a 2D slice of a droplet evaporation problem, very coarse mesh, but it's really designed to be like illustrative. And if you look at the pressure field here, this is the droplet, this is the inside of the droplet, this is the air around it. So if you look at the pressure field here, you can see the pressure is discontinuous at the liquid gas interface, and that's due to the surface tension. So there are discontinuities and fields such as the pressure. If you look at the velocity, which is the other side, velocity is also discontinuous. So what happens is that when you have the evaporation introduces the so-called Stefan flow, Stefan blowing, and that's going to introduce a discontinuous velocity. So you have major discontinuities in your momentum equation from the pressure, and also the velocity itself is discontinuous, and then all of the fluid properties are also, basically everything is discontinuous at the interface. And then for resolving this, we basically use I would say our fundamental philosophy was to err towards the side of discrete conservation. So if you're familiar with finite volume numerical methods, you might know what some of these things mean. If you're not super important, we'll just kind of go through these things quickly. Yeah, so I use a unsplit geometric volume of fluid method for liquid tracing or liquid indicator that has a property of being bounded and discretely conservative, which again is a relevant property that you want to have. We built it on the NGA code, which was a solver that discretely conserves the mass, momentum, and kinetic energy in each phase separately. For the phase interface, you had to implement a lot of fixes to be able to deal with that in a way that was accurate and stable. So chose a mass, momentum, consistent distributive scheme to use at the interfacial cells. And then for the pressure solution, we used the ghost fluid method, which allows for a sharp representation of the pressure discontinuity instead of spreading it out over several computational cells. For scalars like temperature field, vapor field, we use an approach called BQuick, basically, which is based on the quick scheme, which is thoroughly accurate. But then at locations of discontinuity, it degenerates to like a first order operating scheme to maintain stability. And then most of the fusion operators, we just use second order central difference schemes. So really what I actually spent a lot of my PhD thinking about was what is M dot being the evaporation rate. And so I'll talk about that here. So kind of the idea, right, evaporation rate can be predicted, you could say, from energy conservation equation or from mass conservation equation. In reality, both of these things have to be satisfied simultaneously. There's an additional relationship where the temperature and the vapor mass fraction are linked through some type of thermodynamic equilibrium relationship, like Cauchy-Scapron relationship at the interface. And so all three of these equations have to be satisfied simultaneously. And so if you stick them together, you get this nonlinear solver that you have to solve that will simultaneously give the evaporation rate, the temperature, and the mass fractions. Okay. So we spent some time investigating this and looking at various strategies of this and understanding which one is more or less accurate, which one is more or less stable, which one is more or less robust, et cetera, et cetera. So I spent a lot of time doing that. And based on how I implemented, I was able to get a scheme that was not only stable enough, but was unconditionally stable, and not just theoretically unconditionally stable. Like, if you are familiar with numerical schemes, you'll know like you can easily prove that something is supposed to be unconditionally stable, but then if you actually try it, it doesn't work for high values of your parameter, which I'll call CFL number. So I actually tested this at CFL numbers of like, I think 16,000 or something, and I was still seeing good results. So I was like, okay, this is actually unconditionally stable. Okay, so, and then results. So yeah, unconditionally stable, proven convergence against analytical solution, first order. At the time, people were not even proving that their schemes converged. They were just like, yeah, we have evaporation, great. So we were proving actually that we can converge. First order is better than not proving any convergence at all. Our convergence was in the infinity norm. That means the maximum error was actually converging. So most people look at the average error, and then if you zoom in, what you will find is that the error is decreasing far from the interface, and near the interface, error is actually not converging at all. So we actually showed that even at the interface, the most troublesome area, we were seeing this first order convergence. So again, very nice. And yeah, and then I kind of also did some further validations later. Okay, so that was the numerical scheme. So now for the rest of the talk, we'll just kind of talk about how we use the schemes and not necessarily numerical details. So here are some relatively recent work that we did on these things, just showing the power of this to be used in various situations. So in the image A here, I investigated, I'm not sure if you can see the individual gray dots, maybe online, but if you're able to get close to the screen and see them, we looked at interface capturing simulations of droplet combustion inside of homogeneous isotropic turbulence. So we have all of these droplets, and then the flame is this orange contour. Here we did a detailed study of just one droplet, looking at things like how it deforms due to aerodynamic stresses, how that couples with the internal motion inside of the droplet. Here we did a very similar study, looking at how all of that changes the evaporation. And then here we did another study that was similar to this one, but instead of looking at the evaporation of a single component liquid, we looked at a multi-component fuel blend. In this case, this was jet fuel surrogate, a tri-component jet fuel surrogate. And you can see some funny things like the fact that this yellow fuel seems to always evaporate in the front of the droplet or the wind side of the droplet, whereas this magenta fuel appears to mostly like to come out of the rear due to the preferential effects of circulation.
So what's yellow and magenta?
That was a good question. I actually forgot what the colors meant. They are in my SciTech paper. I believe.
But is this multi-component?
Yeah, it is. I believe that they're toluene and isooctane, but I don't remember which one is which.
Oh, okay, so can you explain just briefly? You're discretizing, so you're discretizing in such a way that at every grid cell, much smaller than the interface, a droplet, you have some boundary condition at the interface that describes the mass transfer.
Yeah.
Can you just describe a little bit what that equation is and how that's done?
The equation for the mass transfer.
Just how is it, yeah, how do you deal with the boundary condition at the interface for the mass transfer?
Yeah, okay. So at the interface, we have to solve the temperature equation, like the temperature differential PD, the vapor mass fraction differential PD, and then we're solving that closest equivalent relationship. And so the way that I approached it here was we used we discretized the equation, and so now it's basically converted from a differential equation to an algebraic equation for each of those things, and then we put them together and solve it.
Well, what's the boundary condition?
Oh, the boundary condition, I see. So for the temperature field, if you're going to compare the gas temperature to the liquid temperature, the temperature has to be continuous across the interface. So that's one of our conditions, okay? And then the vapor field has to satisfy a function of the temperature. That's part of like why they have to be solved together. So the boundary condition is kind of like implicit based on the fact that the temperature is continuous and the vapor has to be a function of the temperature, and then both of those things has to be chosen so that their gradients reflect the evaporation rate.
So it's like a Robin boundary condition?
Yeah, I would say like individually, they maybe look like Robin conditions, but because they're all coupled together, I would not necessarily describe it like that. Yeah. Yeah, so yeah, the two fuels, so yeah, this was since I'm talking about, the three fuels were isooctane, toluene, and MDK. And I think that this is isooctane and decant actually. The toluene tended to evaporate faster. Okay, so the next part is mostly work from Meha, looking at droplet evaporation. So basically this type of stuff, and we're trying to understand how the fact that the droplet is not a perfect sphere is affecting the evaporation. So to start off, I actually investigated this analytically. So I enjoyed doing that. That was fun. I learned a lot of math. And so The key things here were I investigated the effect of the shape on the evaporation. And the shape is mostly governed by the Weber number, which is the ratio between aerodynamic and surface tension stresses. Zero Weber number is basically a sphere. Larger Weber numbers, you see them deform into more complicated shapes and eventually break into smaller droplets. And there's a lot that's known about droplets, including that at small Weber numbers, droplets tend towards being ellipsoid-like shapes. This has been studied. However, the real droplets are not actual ellipsoids, they're just ellipsoid-like shapes. So I was actually curious about how the results would change if we did something that was a little bit more realistic rather than a ellipse. And so, yeah, again, I did this analytically. So I solved the steady state version of heat transfer combustion equations and spherical coordinates. I assumed that we had like an axis symmetry. So this is really just a function of the radius and the angle. And then to describe the interface, I have this parameter eta, which is basically like the radius, the effective radius as a function of the angle. So here eta would be smaller, here eta would be larger, like this type of thing. And then I can write eta using spherical harmonics. And this is a perturbative strategy. So I have a perturbation parameter epsilon that I use. So I'm assuming shape is like nearly spherical, but it's not spherical. I don't have to assume that the droplet is symmetric, which is an advantage over ellipsoid modeling since real droplets actually are not symmetric. This is known. Yeah. With the simplifications that I gave, spherical harmonics can be expressed really using Legendre polynomials, which is what I got to here. And then kind of the key aspect was I used this existing solution by Taylor and Akivos, who had done a separate study for a droplet free falling at low Reynolds number. And they basically found out what these parameters H should be for that situation. So if I make my perturbation parameter be the Weber number, then my study lines up with theirs, and then I can use kind of their results to start. That's what I did, and I got this type of result. Non-spherical droplets vaporize faster than spherical droplets, specifically this equation, where this is the solution for a spherical droplet. And you can see this function of Weber number. Some interesting things about it. There's no burst variation term. I thought that was interesting. So the enhancement is quadratic. Or it starts off as being quadratic and it has a cubic term. So there's no linear term. I liked that the result in the end was something that could be written only in terms of Weber number. You didn't need to do like some fancy integral of the angle or anything like that. Weber number is a very easily measured parameter just using the fluid parameters and velocity. So you don't need to do like if you wanted to actually compare it to an ellipsoid, you have to like take photographs or something in order to understand how it's deforming. With this theory, you can just use the Weber number. And we actually investigated the reason why vaporization was occurring. And one of the results was that the enhancement of vaporization is not related to the change in area. It's specifically related to the local interface curvature of the droplets. And this was all shown from the analytical theory. So I kind of spared you actually showing all of those things in detail, but you're perfectly free to, like read the paper if you want. It also did some results for flames, as combustion, All right, so using that, we went on to actually use our numerical method that I talked about before to investigate the question of, well, asymptotic theory is correct for small Reynolds numbers, small Weber number. What happens for a larger Reynolds number, larger Weber number, that might be more realistic to a real system? So that's what we use the high fidelity code for doing. This student, which is Meha, chose to investigate this for in decaying, which is like a kind of a fuel surrogate, a common fuel surrogate. It's used for both gasoline fuel surrogate and aerospace fuel surrogate. And we investigated at this type of condition for pressure and temperature. So it's supposed to be more closer to a aerospace type of configuration. And we wanted to do this, but we also didn't want to do a naive parameter study because these are very expensive simulations. So we had to think about what were the phenomena that were controlling the physics of this problem and really limit ourselves to investigating ones that we thought were the most relevant. So we thought maybe the boundary layer behavior was important. So we chose a couple of key Reynolds numbers. The Reynolds number 25 is for a sphere, thought would be fully attached. Reynolds number 120 for a sphere, thought would be basically fully detached. And then for the Weber number, which are other parameter, for Weber number 1, you're very close to being a sphere. And Weber number 12 is about the largest that you can get without the droplet fragmenting. So we kind of looked at a couple of Reynolds numbers and Weber numbers within that range. Okay, so this is kind of the configuration. I have a droplet inside of this domain. It's initially spherical. Over time, due to the aerodynamic stresses, it's able to deform. So airflow is going that way, and we have made gravity in this direction. And the strategy that we have used is this mimics the free fall of a droplet terminal velocity. So the gravity in the simulation is actually like arbitrarily chosen so that we can get whatever terminal velocity that we want to get. All right, so she did some validation comparing a result for a spherical droplet, so a low Weber number droplet, to some existing correlations, and got, for reasonable error depending on the mesh size that we were going. So we felt like, hey, our mesh is refined and we can use that to do additional studies. And then we went on to do additional studies, and this is a summary of our result. So we saw that even for high Reynolds number, the vaporization rate increases as a function of Weber number pretty much monotonically. These are actually the raw results. So like red, blue, green, black, it's a monotonic increase of Weber number. This cluster is the high Reynolds number, which is 120. This cluster is the low Reynolds number, which is Reynolds number 25. So you're seeing the same result in each case. In the higher case, we actually saw that evaporation rate can be up to 20% higher, depending on the deformation of droplet due to aerodynamics, 20% higher than expected. And we showed that the effect was stronger at the higher Reynolds number compared to the lower Reynolds number. So we thought that was pretty significant. So the next thing we wanted to understand was why this was occurring. This is a high Reynolds number case. Clearly, it doesn't satisfy the same theory as a low Reynolds number case, or maybe it does. Let's investigate it. Okay, so the low Reynolds number theory is showing that evaporation increases related to curvature, and as a result of that, evaporation rate per unit area is actually larger for the deformed case compared to the non-deformed case. So we can actually just extract the evaporation rate per unit area, maybe compare that for all our cases, and that would confirm the theory. So we did that, and that's totally not what the result was. Result totally contradicted, right? So we found that in all of our cases at the same RE, each case with different Weber number had essentially the same evaporation rate per unit area. And so at high Reynolds number, the overall effect is actually due to surface area and not due to curvature. So it seems like, maybe all of our theory was for not very useful. That's okay. Let's just work to explain what we actually have here, not necessarily try to shoehorn our beautiful theory into it. So we investigated this in more detail, and what we found was there was some type of balance between interface curvature and boundary layer separation. Makes sense. So this is a low Weber number case, closer to being sphere. Still not really a sphere, right? It's closer. This is a high Weber number case, clearly not a sphere. So if you're looking at it like from the side, of course. And as we analyzed this further, what we saw was actually evaporation rate here in this droplet is higher than evaporation rate here in that droplet. And that actually does agree with the theory that we said before, because curvature is higher here and curvature is here. So, and this stagnation reason, where the Reynolds number is going to be closer to 0, actually the theory does work. However, we also noticed that on the other side of the droplet, this has a lot of evaporation that you can see, and you can't essentially see anything on this one. So in the rear, there's some type of, due to the boundary layer separation, there's a wake formation and mixing mechanism in the wake that's causing a different type of evaporation to occur back there. And these two things, for whatever reason, seem to happen in such a way that the overall effect is that the average evaporation rate for both cases is the same. per unit area. Because this one has more area, if they have the same per unit area value, this one has more area, so it's gonna have a net higher effect. Yeah, so that was the case, so that wasn't expected, but
Well, these are the residence time, I imagine like the image on the right, you have a lot more recirculation, so you have this. Do you have like a fluid that's trapped, and so the vapor that evaporates just stays there? Or are you constantly training fresh fluid from the back? And
yeah, that's exactly the mechanism for this one, right? So if you, well, I don't have the plot here, but it's in the other paper. Yeah, there's fresh fluid coming in this direction, and then this is evaporating. And then because of the mixing, it's entraining more of the fresh fluid in here and mixing in here. So now the average concentration here is actually much lower than the average concentration there. That means the concentration gradient here is higher than the concentration gradient here, and the evaporation is driven by the concentration gradient. So that entrainment mechanism, which is how the boundary layer separation and mixing effect actually works. Yeah, so that's exactly it, yeah. Yeah, so, oh, yeah.
What you're saying is that there's a lower concentration of water vapor behind that droplet, so that means that you see more evaporation behind.
Yeah,
this droplet?
yeah. Yeah, that's it, yeah. Yeah, so this is a contour of the evaporation rate. So if you show the contour of the vapor or of the temperature, then the phenomenon that we were just discussing would be more clear. I think we have those in the paper. I just didn't include them there. Yeah.
Simulation starts, is it the particle starts out or as a sphere and then you have different uniform flows?
Yeah, so I start them off as a sphere and then they have a uniform flow. And then the Weber number is basically controlled by, because it's a simulation, I can just change the surface tension.
And so you're waiting until it like reaches some steady state, the shape is.
Yeah, and I'm waiting to, I'm reaching some type of steady state. One thing I didn't say here, which is probably important also, is that because this is numerical, I can evaporate without losing mass. I can just basically turn off the mass loss of the droplet. So these droplets all have constant mass, even though they're evaporating. That way, we're not running into some type of effect where this one is evaporating faster than that one. And because of that, they have a different effective size. And so we don't know whether it's the size or the surface area or the curvature. So we eliminated that effect by doing this type of quasi-steady evaporation. Any other question about this part of it?
Yeah, I imagine there's other parameters though that, so there's Weber number, but there's gotta be Schmidt number, right? So the effect of the diffusivity of the scalar. So I guess what else, like, how do you choose those parameters?
I mean, the reason I chose Reynolds number and Weber number, Schmidt number is important, Prandtl number is important, but taking it back to the theory that we already demonstrated, people already kind of treat those as being important parameters. So the purpose of this was to show how the multi-phase aspects add something to it.
But there is some
dependence on
because that'll control the gradient.
Yeah, so those parameters are important. Those are just fluid property parameters.
Yeah.
So as long as we ran the same density, viscosity, diffusivity, which is true because we're using the same fluid.
All right, you'll get, so the idea is you'll get the same trend regardless of what those are because it's controlled, you're just isolating the deformation due to the surface.
Yeah, yeah. So those are important parameters. So we use the same fluid properties. So those are automatically constant in this situation. So really this is just demonstrating the importance of some of the other parameters like the surface tension for predicting this. Yeah. Yeah, so I'll go on. So yeah, this is the result, okay, we don't need to summarize it, we just looked at it. The other thing we looked at was droplet drag. So basically, and it seemed obvious in retrospect after having done the study, but when we were doing those studies of droplet evaporation, we found that the droplets were moving around in ways that we didn't anticipate, and we couldn't get them to have the terminal velocity that we expected them to have. And so that kind of inspired us to think about, well, how is the drag itself being changed by these same parameters that we're investigating? We wanted to investigate it for the evaporation, but how is the drag itself being changed by these same parameters? Okay, and my student Yushu has been doing a lot of work on this. Same configuration, essentially. Okay, and I like going to theory. So this is a theory that Yushu kind of came up with. He was taking a class on interfacial mechanics and had to do a class project. So I said, can you make your class project be relevant to the research? And he said, you betcha, here it goes. And then this ended up being something that was published along with other things at the Physical Review Fluids at the journal, APS journal. So what he is saying here is that to calculate the drag coefficient of a deforming droplet in an effective manner, you probably need to know what shape it actually is, which you can characterize by an aspect ratio, or if you assume that it's nearly ellipsoidal in shape, instead of using the aspect ratio, you can use the eccentricity. But then what he is saying is that from an energy perspective, you kind of have the gas inertia and the liquid inertia and the surface tension forces or surface tension energy being all balanced. Then he writes these expressions, and then making various substitutions and rearrangements of all of these expressions, eventually he gets this, which is a nice equation. So what we're showing here is the relationship between the Weber number, the eccentricity, and also this is the density ratio that we talked about before. This is the viscosity ratio that we talked about before. And interestingly, these two parameters seem to be grouped together in such a way that they are equivalent to the Ohn-Source number, if you're familiar with what the Ohn-Source number is, okay? And so the value of this, I mean, people kind of sometimes get hung up on the actual equation. The value of this is not to actually use this equation. The value is to show from first principles that there's a relationship between Weber number, Ohn-Source number, and this is the eccentricity, but we could say aspect ratio, right? That's really the value of this. This equation is essentially unusable in its actual form, okay? So based on this insight, we were doing some simulations and we tried to actually investigate some of the effects of those parameters. So he, in this case, looked at the density ratio and the Weber number. Okay, and the reason that we looked at the density ratio is because by changing the density ratio, that promotes internal circulation inside of the droplet. And then that naturally leads you to ask the question, how do you measure the internal circulation? So originally we looked at like the maximum velocity. Maximum velocity is very like a sensitive parameter. If you just check maximum velocity, it's very sensitive. So you'll see a lot of anomalous spikes and dips and those things. So we needed some average parameters that can measure internal circulation. So we looked at several of them in our AIAA SciTech conference paper. And so mean vorticity, mean absolute value of vorticity, entropy, and a parameter that I made up called Hill's constant. So if you're familiar with this Hill solution to spherical vortex, which some of you might, some of you may not, that solution has a certain constant, which is related to the vorticity that describes basically the entire flow field. So if you kind of assume that that is accurate even for non-spherical droplets and use the same strategy, you can kind of back it out and solve for that constant. So I call it the Hill constant. So we're still not convinced what's the best way to measure internal circulation, but we're seeing this monotonic trend in all cases, which is what we actually care about. So you have this black, red, green, orange, blue. In all cases, you're seeing a monotonic trend that as you change the density ratio or the pressure ratio, you're seeing an increase in the parameter, and all of them have the same monotonic trend. So without having to discuss which one is the best measure of internal circulation, we can clearly see there's a clear relationship between density ratio and internal circulation, which is what we actually wanted to prove.
back to the last one, what's with like the spikes that happen between 4 and
Yeah,
6?
what is going on with the spikes here? That is a very interesting question. We're not entirely sure actually what's going on with these spikes here. Yeah, I'm not entirely sure actually. So that's a good question. So going forward, oh yeah.
So the density ratio, is it of like the density of the droplet with respect to its surroundings or the other way?
I forgot how he characterized it here. But what we're doing in the study was basically pressurizing the system. And then if you pressurize the system, the density of the gas will increase and the density of the liquid will remain the same. So what this is showing actually is like regular pressure, like 4 times the atmosphere, 10 times the atmosphere, like this. That's what's being shown. I forgot which notation he used for the density ratio, but if you know one of them, then you know. So I talk about the conclusions in terms of that Noah having that knowledge. That makes sense. Yeah.
But this is, so you're showing the time evolution of these average quantities, right?
Yeah,
Um,
spatial average, yeah.
right. But eventually it reaches some steady state.
Yeah, so
So everything you're showing up to steady state is just a transient from a sphere deforming into its final shape.
yeah,
So yeah, I guess there's.
Yeah, so we might argue
there's
that
some
these-
artifact of conditions.
yeah. So yeah, there are gonna be some artifact of like how it goes to that behavior, but I don't actually know like what was happening at that instant. Like, was it moving? Was it like a vortex instability? Like, did the shape change and then kind of, because what the droplet actually does is it kind of like springs out and back and forth like this for a while, and then over time that behavior decays. So was it like a capillary incident, or that's what I meant when I said I don't know what's happening with that. Well, it's good. So yeah, we measured the drags, and what we saw, if you look at the raw data, so dashed lines are raw data, solid lines or corrected data. Look at the raw data, what we saw was a significant effect, in this case of Weber number or droplet shape on the drag. But if we measured the actual frontal area of the droplet and normalized it, then all of these curves collapse. So that's actually kind of weird because we still use the drag coefficient of the sphere to calculate this, but we didn't use the drag coefficient of the disk or anything like that to calculate it. It's actually kind of weird that they collapsed so well, but apparently they did. And we tried to do the same thing for our study of internal circulation. And you can see a similar result, but the collapse is not as great. So there's more variation. There's something else that is important that's driving the drag effect for internal circulation. It's not merely the shape of the droplet. Okay, so I see that I'm getting close to the end of my time. So I think really what I wanted to talk about today was a more recent work of the same student, Yushu, and how we've expanded that. And so he has this paper at ASME soon in Portland, and then also at the upcoming APS conference. And the idea here is that we're going to take some of those results, understand their implications in turbulent flows. So, for example, we know the droplet deformation increases drag. Well, what that's going to mean as a practical matter for spray, the trajectory of droplets is typically miscalculated in spray. The physical location of the actual fuel is not known. Because the droplet deformation increases the droplet evaporation rate, that's going to mean that the vapor concentration, vapor mixing are miscalculated, so the combustion is not known. And then the other thing that we kind of notice is that these effects can be quantified by parameters like Reynolds numbers and Weber number. And that means we can have kind of universal models of this, universal meaning like basically non-dimensional numbers, models of these things. So what we did here was we took one of the drag models for non-spherical droplets, and we put spherical droplets in homogeneous droplet turbulence and freely deforming droplets of the same size and homogeneous isotropic turbulence, and then compare their dispersion. Okay. And to talk about the dispersion, we introduce a couple of parameters that are probably well known to people who draw particle-laden flows. So we have the particle autocorrelations, and we have the dispersion, or the mean square displacement, which you can calculate from the autocorrelation. Okay, and in this case, we solve the droplets using a Lagrangian particle simulation approach rather than an interface capturing approach, if you are familiar with that. And so in that situation, the gas field satisfies standard Navier-Stokes equation, where the liquid field is considered to be isolated droplets that satisfy something more like Newton's law. The position derivative is the velocity, mass times acceleration is your force. In this case, the only force is the drag. So the force is the drag. Okay, and then for the drag, we took the classical Schiller-Naumann relationship to represent spherical droplets. And then for non-spherical droplets, we used a existing simulation database from Hellenbrook and Edwards to get a drag correlation, where the drag is going to depend on this is the aspect ratio, it's going to depend on the viscosity ratio, and the Reynolds number of the droplet. And then the aspect ratio itself is a function of the Weber number. So that ties it back into everything we've done previously. Okay. So if you're not familiar with HIT, you have like a triply periodic simulation domain. You have a bunch of droplets in there. You have a fluid flow that's going around. In this case, I'm visualizing the fluid flow using vorticity. So you can see the vortex structures in this flow. Okay, we use these parameters and results. All right, so preliminary results. We looked at the autocorrelation and we saw this type of data. So trend wasn't super clear here. So we actually have two versions of this. The version of ASME that we did originally, just looking at the autocorrelation, we had a very clear trend. This newer version, which is associated with APS project and has slightly different parameters, trend is not so clear on autocorrelation. So we ended up having to actually construct the dispersion of the particles. So in this case, I don't think I said that before, dashed or dotted lines is a spherical droplet. These solid lines are droplets of the same size, but using the other drag model that accounts for Weber number deformation. And the trend that we're really seeing is that at least at early times, all of these solid lines are above all of these dashed lines. In other words, all of the spherical particles have more dispersion than all of the dashed particles. At later times, it becomes more dependent on the diameter as to what the trend is. But I want to point out that you should have some care in interpreting this, perhaps. So because this is HIT with periodic boundary conditions, you can have a situation basically where a particle was here, it leaves through, like, let's say this left boundary, because it's periodic, it would come back into this right boundary. So really you want to think about perhaps what does the trend look like in the range of times where the particles haven't done that yet? And that corresponds entirely to times that are less than here. So within that time frame, the non-spherical particles are systematically more dispersed than the spherical particles. We aren't quite sure how to interpret the data beyond this yet, or even if it makes sense to interpret the data beyond this yet, but just decided to show it. Maybe some of you have some ideas about.
So what PK Young does when he looks at dispersion is he has periodic boundary conditions for the fluid, but not for the particles.
So they escape.
So, well, they just disperse out, but they always, as they move further out, you always know the fluid velocity field because it's periodic. But then you can just measure, you have an initial clump of particles that are dispersing out, and you can go indefinitely out now. So you just don't apply the periodic boundary conditions to the particles. And then when you know the particle location, you can figure out the fluid velocity by just knowing the periodic length of how far it's going.
Yeah. Yeah, okay, that's interesting. We might actually do that. And there might be some way of actually saving this data, like talking about it.
No, you could use the exact same data, it's just
Yeah.
you have to not image it back. right? So
Yeah.
so you have to know if the particles did pass.
Right.
So it actually might be tricky.
This is a four-way coupled simulation, isn't it?
This simulation is four-way coupled,
Yeah,
yes.
so that won't work in a four-way coupled. You need to treat that the force, right? Particles.
That's right, that would only work with one-way coupling.
Yeah, I see, yeah. That makes sense.
So what you would do is have a big domain, start particles near the center,
Yeah,
and then disperse out until they reach the domain.
Yeah.
And you could remove them once they leave the boundary.
so yeah, that's, I mean, this is why we're here to discuss really this type of thing. Yeah, so that's, okay, so here's some additional stuff. So initially, one of the hypotheses that we had was maybe dispersion is higher because the non-spherical droplets, which have a different drag law, might subsequently have a different particle response time and therefore have a different Stokes number. So we measured the Stokes numbers and they're basically the same. Dashed lines, solid lines, they're basically on top of each other. Another idea is that the Weber numbers could be different. So we measure the Weber numbers and they're basically the same. There's more variation for this case in red, which is the highest diameter, but they're still basically the same. And then these are very identical.
Sorry, the spheroids, are they dispersing faster?
Yeah, the spheroids, those are the ones that are not spheres. Yeah. So yeah, maybe we should change the terminology. Yeah.
No, but it must be due to alignment, right? Is that what you're getting to?
Yeah, I mean, we still aren't exactly sure what it is for the dispersion. So you're saying
Like people look at like rods and turbulence, they tend to align. with the
Preferentially
rods,
align,
Right,
yeah.
so that could then affect their local drag, and so you can imagine the particles are just sampling different parts of the turbulence.
Right.
They're aligning and then moving faster out.
right.
Is if you're capturing those effects, that might be what it is.
Yeah. Yeah, I mean, that's a good hypothesis, right? So that's something that, like you said, in the literature that exists. I haven't seen it as much for like HIT, but I've seen a lot of literature and like more other types of flows like pipe flows or
Yeah,
like
channels.
in type of channels or in type of like rotary flows, like vortex flows. I've seen exactly that result. That's kind of the direction that we were planning to go, but we haven't gone there. So as far as this kind of initial result is concerned, that's actually it. Like, so we have more dispersion, and this dispersion is directly related to the particle shape and its effect on the drag. It isn't caused by some type of like implicit parameter where the shape changes the Stokes number and the Stokes number changes the trajectory. The shape changes the Weber number and the Weber number changes the trajectory. It's in some way directly related to the properties of the drag. And that was kind of the final results that we had there. Just and yeah, overall summary, we basically did a lot of studies. They were based around the idea that standard theory of droplets and sprays makes a lot of incorrect assumptions. Using theory numerical simulation, we can kind of relax these and get a better understanding. So droplet deformation increases the drag and enhances the rate of droplet evaporation. And kind of more practical, perhaps, a noticeable effect in droplet dispersion appears when you are doing this in turbulent flows. And we're planning to do evaporation as well. And so then we'll be able to prove the effect that this had on fuel mixing. So I think this is going to like make it more like practical, maybe. So that's the idea. We started off from a very fundamental, like this is interesting idea. And then we're kind of trying to build up towards, okay, this is how you actually would use this. This is why it actually matters for your engine. Okay. And that's actually my last slide. We can thank, various sponsors. These sponsors were not necessarily for these projects. These are just literally every sponsor I ever had. Okay. And then this is a group. Okay. So people have been kind of asking questions as we go, but we'll have more time for questions now.
Any questions?
Oh, so you introduced that one non-dimensional number like OH.
Yeah,
What was the circumstance that non-dimensional parameter originally arises? Because I think it was like the density ratio divided by the viscosity ratio squared. But if both of those ratios are already non-dimensional, like in what is the circumstance that requires that form of the ratio of ratios, so to speak?
Right. So originally it wasn't a ratio of ratios, it's just kind of like, for our case, based on how the problem is non-dimensionalized, that ratio is equivalent to the only source number. The original application of the only source number was in like droplet, like if you have like you can think about printing, like an ink droplet or something falling down. So originally it was designed to measure that type of thing. And it's supposed to be a ratio of surface tension and inertia of the droplet. And the time scales kind of work out such in a manner that it ends up being equivalent to that.
Maybe you have mentioned this, how do you verify the numerical code? Are they compared to any maybe experiment data? Or theory, but you already say some theories are not correct.
Yeah, so we compare it to theory by doing simulations of spherical droplets. So the theory is very accurate for an isolated spherical droplet, because that's what the theory is written for. So we compare it to that case, and that's one way of validating. We also looked at like semi-empirical correlations based on experimental data for like a spherical or nearly spherical droplet in a forced convection type of flow. We did some validations associated with that as well. I mean, that's like kind of basically the best data that exists, at least for droplet evaporation and droplet.
There's been some experiments in homogeneous turbulence that I think Ferrante's group may have compared to, and I thought it was like, I wanna say it was like ice or something that was like, it was a way that it was really easy to control. And there was the time scales of the evaporation were fast enough, and they could visualize it really well, so they actually had, it wasn't a liquid droplet, but it was a way to validate some of the themes.
Yeah, that exists as well. So most or really all of the studies that I've seen where people are experimentally looking at droplet in a turbulent flow, the length scales are kind of inverted of what would be useful for my application.
Yeah.
And that they're usually looking at droplets that are big, in the sense that the droplet may be like 5 millimeter, 10 millimeter, like larger than the turbulent scale. And I'm looking at the opposite type of thing, where my droplets are coming from the other direction. They're smaller than the turbulent scale, but they're kind of growing up to that size, rather than the case if they're bigger than the turbulent scale, kind of shrinking down to that size. So yeah, I could look at more of those things for validation, but I mean, just to have more data. But because it's kind of like sometimes the opposite case, I didn't. Yeah.
So when you're looking at the transient tracking of the deformable drops, right?
Yeah.
I couldn't catch it, but like, are you tracking the orientation of the eccentricity?
Yeah, so that's a good question. So for the initial study that we did here, what we did was we assumed that the droplets instantaneously orient with the flow.
Okay.
So that's equivalent to assuming that the capillary time of the droplet is faster than the turbulence length scale, which is fairly accurate for smaller droplets, less accurate for larger droplets. One idea that we actually already have the code for it, but we haven't tested it yet, is to use something like a tab model to reflect the time variation of the actual the time sensitivity of the process of adjusting to the flow.
What could be interesting is you have the spheres and spheroids, you can compute a PDF of the slip velocities, right? And what you'll probably find is the spheroids are aligning with the flow, and you might be just having lower slip velocities, which leads to more dispersion.
Yeah, that's what I was thinking originally. That's why we looked at the Stokes number. That's what I kind of thought, right, is that if they preferentially aligned in such a way that they kind of have lower slip velocity, then they should have a lower Stokes number,
But I
right?
don't think that the Stokes number is gonna be based on some a priori estimate of the timescales.
So this Stokes number is not. This Stokes number is like calculating the instantaneous drag coefficients and then inverting that to get the response time.
Huh.
Yeah, so that's what we did here. And in our other study, however, we did see that the Stokes numbers were noticeably different. So it seems like everything is kind of dependent on the parameters and sometimes, which is typical for turbulent flows, right?
These are average Stokes numbers.
These are averaged over the class of all droplets of this diameter, all droplets of this diameter.
Is
Yes,
the standard deviation also the same between spheres and spheroids?
I mean, we've never calculated it, but I am
A
very,
PDF could be.
I'm very interested now in calculating that. We've literally never looked at any of the statistics other than the mean. Because the mean is kind of all we need to calculate things like this, so we just look at the means.
But the
Yes.
dispersion is literally the mean square displacement, which is related to a standard deviation.
Yeah, we computed it from this, which is also kind of a second order parameter, as your point. Well, it's the mean of a squared velocity, basically. Yeah, but we haven't looked at any statistics like standard deviation or, you know, skewness, kurtosis, any higher order statistics. So yeah, I think that might be a really good thing to show. Maybe the standard deviation, even though mean is the same, maybe standard deviation is much larger
Or it's skewed
or skewed towards one side. Maybe there's some type of skewness in the distribution. Yeah.
Well, it's after 5. If you have any other further questions, you can chat with John afterwards. Let's think.